Okay, so here's part 2 of the protein chapter, Workers of the Cell, as it's subtitled in your book. And we had introduced the different amino acids in the previous webinar. We talked about, of course, the needs of protein in our diet with respect to the essential versus non-essential amino acids. And we're going to continue on here with peptides and proteins. And so we had ended last time with an alanine-alanine kind of dipeptide breakup. It was the hydrolysis of that dipeptide via a protease to create the individual units. And here, just want to revisit that again, but instead of using alanine and alanine, we're using alanine and valine. So here would be an example of that union of that peptide bond forming by virtue of the carboxylate on the alanine and the protonated amine on the valine. So they come together, they form a peptide. What kind of peptide is this? This is a dipeptide, right? Because there's only 2 amino acid units there. And again, remember that the carbonyl with the amine structure together create what's known as the amide group, where there's a bond between the carbon and the nitrogen, okay? So that's all part of that kind of functional group, the amide bond. The N-terminal versus C-terminal. This is some interesting nomenclature that is extensively used and in any kind of virus, bacteria kind of research going on, including now even with the coronavirus and any other type of virus or even DNA structures, all this stuff. They're going to be talking about the N-terminal or the C-terminal. The N-terminal refers to the protonated amine, the positively charged, and the C-terminal or terminus in this particular case corresponds to the carboxylate group, so that negatively charged end point, okay? So if you look at the alanine valine, by dipeptide that we formed up here, you can see that the first cartoon with this N-terminus being the blue, the alanine, and the orange valine as the C-terminus does correspond to the peptide that was formed in the upper right part section here of the slide. Why? Because the N-terminal is positively charged. That's where the positive NH3 is of that dipeptide link. And then the C-terminus is the carboxylate, the negatively charged. Know that it is not the same, that this connection here is not the same as just saying, hey, what about the N-terminus of valine? Well, because that's not what happened. The N-terminus of valine is actually in the middle and it connected with the C-terminus of alanine to create that amide group. So you can see that those are definitely 2 different types of peptides if they were unioned as such. All right, so I think that's pretty straightforward. But generally speaking, you move from polypeptide to protein if you're talking about more than 50 amino acids. So 50 or more, this is just a general nomenclature. Dipeptides are the smallest amino acid compounds. Again, I talked about you don't have a monopeptide because that would essentially, well, it's not correct because you don't have a peptide bond first of all, but then that would automatically default you to having just an amino acid, a single one. All right, so if we're having groups of amino acids come together, these peptide bonds are formed by virtue of the combination of the various different types of amino acids, and there's obviously molecular machinery that can do that. So now let's start looking about, well, what do these shapes look like? And so we're going to organize these shapes into 4 different classes. And here we're going to start with the primary structure. So the 3D protein structure. And this is really important because this is essentially the backbone of what we're doing and therefore the baseline of what that protein structure looks like, at least on paper, okay, is to see what kind of sequence that these amino acids are connected. So let's look at the primary structure of angiotensin 2. It's a peptide that regulates blood pressure. Here is this beast, right? You have all of these different side chains, but the side chains that are shown in blue are just based off of these individual 20 amino acids that we already introduced, okay? And these amino acids are then shared by amide group linkages, the peptide bonds, right? And so if you start from left and moving to right, so we'll start with the N-terminus, where you have this positively charged protonated amine, you have also the carboxylic group that would have been there. Again, it's not in blue. The blue is part of the side chain. You have the carbonyl attached then to this amine group or amine group, and together they form the amide group, right? So you have the kind of trigonal shape with the trigonal shape gives rise to that amide group functionality. And it just continues on that whole line. So if you were going to look at this angiotensin 2 peptide, you'd say, well, you know, what does it look like, and how would I refer to that as? Well, this is just 8 amino acids. So although it looks big, you know, would you really consider this to be a protein? Well, again, proteins are generally going to be classified as maybe 50 or more amino acids, so you really wouldn't do that here. You would just say that it's one of the peptides or polypeptides that exist in the body, and that, you know, in this particular case, this angiotensin 2 is responsible for some of the blood pressure regulation. So you would start off with the one on the far left, and you would identify them by the side chain. So you have one side chain, and I'm counting from left to right, and I'm indicating with the blues there. You have 1, 2, 3, 4, 5, 6, 7, and 8. So you have 8 total up there, and guess what? Angiotensin, we have 8 amino acids. And using the 3-letter code to designate which those amino acids are, you have aspartic, right? You have arginine. I should say you have aspartate because it's an ionic form, it's acidic, and it's also polar, right? That's the very first one. You have arginine, valine, tyrosine, leucine, I think, isoleucine, histine, proline, and phenylalanine, okay? So you have all of these, right? And this would be the nomenclature if we were to use the single letter code. Again, you know, for aspartate, they use the letter D to indicate aspartate because tate sounds like date. Remember that crazy stuff? Anyway, you can look at it in the other webinar preceding this one. Of course, it's also in your book like that too. A little bit strange, but you would label that if you don't want to have all these 3-letter, you know, names for each of the amino acids. You would just have it singly coded as D, R, V, I, H, P, and F. Now this here, okay, this connection, the way that these are connected, we have to start somewhere. So this is our baseline. This is our baseline structure, and this is called the primary structure, and it's indicated with this, you know, number 1 with a degree sign. Okay, so always the primary structure is essentially what the peptide backbone is. In this particular case, you're going to ignore the side chains. Okay, you don't, because you have to identify what those are if you're actually going to give names for them. But just know that that's what the peptide backbone is. Okay, so how many are there essentially? And then you can fill in all the other side chains if necessary. The more important part here is the secondary structure, and this gives rise to the alpha helix. So the secondary structure is talked about in terms of that backbone that we just had, kind of like almost in the Lewis structure. You know, it's again not really a skeletal structure because all the hydrogens were shown, or a lot of them were anyway. But we're talking about now trying to orient these into more of a 3D looking kind of framework. And so this is going to give rise to helix patterns. Okay, so you have, for instance, in this cartoon on the left, you see you have the C terminus on the bottom, you have N terminus on top. Again, C terminus means you have that carboxylate, it's charged, it's on the bottom in this case. The N terminus is positively charged, it's that protonated amine, it's on top. You have carbon, oxygen, nitrogen, you have an R group represented by a purple sphere, and you also have hydrogen. All of those are going to be part of that ball and stick model there. Also shown within this kind of structure here is the hydrogen bonds. Okay, so you have hydrogen bonds even aligned within that same backbone. Okay, you have obviously the red spheres are indicating oxygen, the purple spheres are indicating, you know, an R group, and then you have the gray spheres indicating hydrogen. That dotted blue line on the left-hand side in that colorful ball and stick model indicates that you have some hydrogen bonding between the oxygen of one side chain species and the hydrogen of another side chain species. Again, what type? Well, we're going back to that angiotensin 2 peptide, the polypeptide that we discussed in the primary structure in the previous slide. If you were to, you know, look at where all the possible connections are, you could probably map that out, and that's what's done in this, and in the right image here, that cartoon with the banded arrow, you know, the helical arrow, you know, going upwards, and you have the carbon, oxygen, then you also have the hydrogens. Again, that's where the hydrogen bonding is going to occur. Okay, hydrogen, oxygen, nitrogen, and fluorine. Those are where all those hydrogen bondings occur. And it's important that you know that this helical pattern is then generated by virtue of those hydrogen bonds. I think that that's important to make sure that you always remember. Okay, so anytime you see any kind of helical pattern, know that it has formed due to hydrogen bonding action. Okay, and again, within the same backbone. And where is it at mostly? Look, it's between the carbonyl. It's between the carbonyl of, one of the amino acids and the amine group of another one of the amine groups that are within the polypeptide, okay? So you have the partial negative and you have the partial positive, and they're going to give rise to all that. Can you have other linking between some of the side chains? Yes, you could, but here in this particular case, these helical patterns are generally going to be derived, okay, from the amino acid, carbonyl, and amine groups that naturally exist, that have been established in that primary structure sequence. So obviously a coil is pretty important. It can flex, right? Obviously, these things are not going to exist in free space. There's going to be water around it, and proteins are amazing at holding on to water. And they can generally, for instance, I'll show you in a future demo that I have, that the casein from milk can actually hold on to water quite a bit. I think it's for every one gram of casein, which is one of the proteins that makes up milk, it can hold on to about 3.5 grams of water. So pretty good stuff. Multiple hydrogen bonding render it along in a strong structure, and it can still flex and coil. Okay, side chains are going to be oriented outwards from the helix axis. All right. Here's another example of a secondary structure. Now we're going to talk about beta sheets, okay? And the beta sheets now have to do with everything in between, all right? So you had that long axis. Now you have an extended structure that comprises multiple backbones. They're all arranged in a zigzag structure, kind of like a folded paper fan, if I can kind of give that kind of assessment there. And you have the R groups, and they alternate from front and back. Why? Because of steric arrangements, just the lowest energy configuration. Can't have too many side groups all of a sudden overlap into one plane or one area. Like, it's kind of like the cis and trans, right? The trans is going to be more stable than the cis kind of arrangement if we're talking about, for instance, double bonds and with, positioning of different R molecules, and of course H, cis and trans. Cis is the higher energy formation, so that will generally not be preferred. The trans is definitely preferred, so that's why, again, here you have all the side chain groups denoted by R just being, positioned in and out of plane, front and back. So here, this is the way that this beta sheet is set up, okay? And you have hydrogen bonding between the amino acids, between adjacent backbones. So pretty cool nature here. So you have more than one backbone, right? And you have them all still connected by virtue of hydrogen bonds. So again, the hydrogen bonding was the third most powerful intermolecular force, right? We went just non-polar bonds were the weakest. Those were like the van der Waals or the London forces. And then we increased there a little bit with dipole-dipole type of forces. So that would be very common in ethers. Then we have hydrogen bonding. Then you have ion dipole, kind of like salt and water. And then you have salts, actually, which is that ionic attraction, which make up the strongest intermolecular force. Again, the hydrogen bonding ranks third in that scale. And it's so strong that, or I should say, it's at least strong enough that it gives rise to not only helical patterns and geometries later that can set up, but then between the different helices, you can also then get, these beta sheets. So that are obviously more than one of those helix. And so that's what that gets, labeled as. All right. With respect to Alzheimer's disease, this actually is affecting the secondary structure. So here's a helical beta amyloid, 42 amino acid protein fragment, okay? So here is a beta amyloid. That's just this general shape, okay? And it's all done in this helical pattern, and then you have some additional residues there that are not participating too much here in hydrogen bonding, all right? But this gives rise to all these different beta sheets, right? Here is what happens whenever you have the plated beta amyloid, whenever they're essentially flattened out and all of a sudden they start to overlap, okay? And whenever they are starting to overlap, then this is a bad thing. This is now considered a plaque, where you have these individual, helical fragments, if I may here, these protein fragments that have great and defined structure and spatial separation from another one, and all of a sudden now they've just been smeared over, and there is no distinction then among some of these fragments. They get kind of flattened out. Maybe there's some overlap. There's a bit too much bonding going on, actually, hydrogen bonding. So, you know, in these cartoons here, you have, you know, the images of the neurons, and then you have these tangles here, and then you also have this, what's known as, I guess, the beta amyloid plaque in this brownish kind of cartoon. This is what is, you know, leading to disconnects, right? Because if the neurons can't fire effectively because there's something in the way, or there's inhibition of the electrical signaling, and we already talked about neural firing, I think in chapter 8 or so. I think I started off with that. Then, you know, you're going to have disconnects in linking, or at least trying to recall certain events from the past, right? And so that's part of what's going on here. So, and then let's move on. We have now tertiary structure. Tertiary structure has to do with the folded protein shape. And the folded protein shape, yeah, look at this. I mean, it almost looks like spaghetti gone wild almost, right? So here's a strand of spaghetti that looks like somebody was playing with here. This, and notice how we say we have a folded protein shape. So we're talking about pretty large protein or polypeptide polymers, if you will, or molecules. Generally, you're going to have more than 50 amino acids in them. And whenever you have more than 50 amino acids, you stop referring them to really polypeptides or any kind of enzymes per se, like any kind of like polypeptide enzyme. But now you're starting to talk more about this overall protein structure. If the protein gets then so long, which this one is, all of a sudden, all of those side chains start to impart some additional, what's known as steric constraints, or additional hydrogen bonding possibilities. And this is where this is happening. So you look at some of these side chains and you have some like hydrophobic interactions. Let's take a look at that on that far right, where you have those two phenyl groups, you know, meeting each other. You know, notice that you don't have any coils in there. Notice how it goes from a coiled kind of setup to now just a straight chain, and then it resumes its coil makeup whenever you see the disulfide, you know, discussion there. That non-coiling represents then a non-polar environment. If we go back up, you know, to look at the hydrogen bonding to water, you know, you can see, well, you know what, you are starting off with a kind of a single strand here. Nothing's really in helical format. That means that you don't have enough hydrogen bonding within those first sets of amino acids that are connected in there. Maybe, you know, there could be 10 of them or so, or maybe even, you know, 15 or 20, but they're not able to hydrogen bond with one another just by virtue of whatever that environment is, and steric hindrance. In other words, where the other molecules, not only from that protein shape, but also from the solution in which it's in, and if there's any other external molecules that are around that are giving rise to the lack of hydrogen bonds that would have been able to create this coiled-like pattern. So you have these straight chain, although it's kind of warped here, start of that molecule, right? You then sometimes have the coils. Again, so if you're starting to look at the coils, know that hydrogen bonding is able to happen. And if it's not, know that there's probably a pretty good amount of non-polar activity going on. Now, on the ends of those groups, even though you don't have any coils here and you have that phenyl group, actually it's a phenol aromatic group near the top of that structure there where it says hydrogen bond to water, and you have a water molecule. You actually have two of them. One on the left and one on the right there at the very top. And one of them is you know, you have some hydrogen bondings of each of those different water molecules to the different hydroxyl groups of each of those different side chains, right? So those can still participate in hydrogen bonding, but that's with the solvent. That's not within the protein itself. And so again, this is one of the reasons why it's not coiled. So you can just take a look at this. It's pretty interesting how that can happen. You do have some interaction, like even between chains, even if there is some hydrogen bonding going on, and then even there might be some nonpolar stuff, like look at the disulfide bonds that occur here. So that can even occur with, you know, within a region of a protein that actually has a pretty significant, you know, nonpolar environment, but yet still gives rise to some of the hydrogen bonding. It might be weak, but there still might be some. And you even have salt bridge formation that even can occur between the two coils. So I think that that's pretty interesting. So you see how you have a couple coils that are connected with ions like that, where it says salt bridge. You can see how that is. You can have hydrophobic interactions. You can have, disulfide linkages. And anyway, the whole point is the tertiary structure can get complicated. And sometimes it's going to be, coiled up. If it is, then you know that hydrogen bonding within that peptide backbone is going to be strong enough, But then if it isn't, then you know that the nonpolar regions are dominating, and maybe it's getting influenced by the solvent or other types of molecules that may be nearby. And that gives rise to the tertiary protein shape. So I think that that's pretty important. So you have the, the nonpolar forces in play here. You have the polar forces in play here, salt bridges, all that stuff, disulfide bonds, everything. Okay. Now, during folding of a protein, what is called a folding of a protein, disulfide bonds, which are covalent, by the way, can be produced via redox reactions. So this is pretty cool. So you have then two individual amino acid segments, all right? And the SH group is known as a thiol group. You have the protein backbone, but I'm talking about just these two amino acid groupings that are the same. They happen to be the same, that just happen to be near one another. Not necessarily with connectivity, but as you can see here with the protein backbone, the backbone is then curved. All right, so you have one of these amino acids that has a thiol group kind of coming around and being bent over, right, and in contact with another amino acid that has a very similar, thiol group. What can happen is that these two individuals can actually link up and form a larger entity, okay? If it's going to be a larger entity, it's generally going to be oxidation, including with the loss of hydrogen, which this has whenever you move from two thiols to one disulfide link, okay? So you have the ability now to have some influence on certain amino acid functionality with respect to making a reaction proceed one way or another way. Guys, this is really important for talking about hair of all things. I mean, I know it's not medically, there, but that's what this is about. It's about knowing that you can alter that folding process, that natural folding process of a protein, and these larger molecules, these more connected molecules can develop. So you have globs also with respect to the globular shape, like myoglobin, which stores O2 in muscle. Okay, you have all these globs too. You have the C terminus in this cartoon of this myoglobin here. You have the N terminus as well. Here would be, again, they're showing you that the exterior surface is polar and it faces the water. But if you look at this globular, you can immediately tell that the hydrogen bonding within the helices is strong, right? You don't have too many regions within this glob that show you that you have a huge amount of non-polar activity. Mostly you have polar activity, and especially in the form of hydrogen bonds that's able to keep those helical fragments, I guess, if you will, or geometries intact. Do they all align in one direction? No, because everything is still this. Again, we're talking about a protein that's going to be big. Things are going to be able to fold. I mean, that's just the way it is. It's like I don't know. It's like stacking. It's like I don't know. Trying to connect like Legos or something, or if you blow up a balloon and it's a really long balloon, of course, and you keep on blowing air into it or whatever, or if you have, I don't know, some kind of stick and you just try to make, the longer that it gets, basically whatever visual you want to think about, obviously it's going to start bending and bowing and folding over and things like that. It's no different than with the protein. So again, the polar amino acids on the surface, solubility in water is going to be quite good. Okay, you know that this is going to be quite polar and then therefore soluble in, for instance, our blood, right? As such, globular proteins tend to have a non-polar center. Why? Because the polar region is facing that which is going to give rise to solubility. Okay, so enzymes and cellular proteins are definitely globular. We'll get back into this in just a minute. Let's talk about fibrous shape, okay? So here you have alpha keratin, you have tendons, and you have dentin, okay? Dentin, again, is the underlying soft structure of enamel in our teeth. The tendons are what helps connect, right? Some of those, the muscle, right? So you have the muscle that's connected to the bone, and you also have, ligaments too, that do that obviously, and then you have the ligature that also connects bone to bone. So all of that, right? Tendons and ligaments. You have the alpha keratin, which is in our nails, our hair, and you have the dentin structure, which is underlying in the enamel, all that stuff, okay? The keratin is generally going to be in these helical shapes, right? It's going to be bundles of them. They're going to be tightly wrapped, and they're going to be pretty much in a uniform direction. Collagen found in the knee joint connective tissue, well, that also contains modified amino acid hydroxyproline, right? That's also a type of helical bundle, really. That's everything is wrapped into it. Notice that this looks way different than the globs that we just showed on that previous slide, where everything's kind of just oriented all over the place. If it's polar, if it's highly polar, and if it's in a polar environment like water or like blood, then that non-polar is going to be in the center, but you're going to have all this kind of globular. Here, this stuff is more directional in terms of alignment, and it's tight packing, and it's not that globular shape. I think that that's the most important part. Anytime you have that, then you're going to have what's considered a fibrous kind of environment, okay? These are mechanically strong, and they're generally insoluble in water. You can easily envision that because there's not going to be anything. There's no space. There's no necessarily, it's not necessarily polar on the inside or outside. It's just, this is just what it is. You have very strong bonds connecting all of these helical patterns. It's more than just hydrogen bonding. You might even have some salt bridges that have formed as well as some ion dipole stuff. So I mean, these are going to be some very tough proteins, and a large time, or most of the time, then you're going to have the side chains, which could be very nonpolar, directed outwards then. Okay. And now here you go, you have the quaternary structure. So why are we introducing quaternary structure? Well, because if you have an abundance of just, of protein units, or sometimes they're actually called subunits, sometimes they're called polypeptides, and then they're all going to get grouped together, well, you're going back and you're looking at, for instance, hemoglobin, which has 4 of these protein subunits, right? You have one in red, one in blue, one in green, one in purple. You have all of these red blood cells that deliver oxygen from the lung via the hemoglobin, right? Each one consists of 4 subunits, each having a heme group, and you remember that the heme group has the iron in the middle, plus 2 oxidation state, right? And this is in a porphyrin ring. By the way, this porphyrin ring, again, that's not a protein, that's just a heterocyclic aromatic organic compound, right? But there is no protein action there. You don't have the amide group functionality at all anywhere in that structure. So you don't have the carboxylate, you don't have the protonated amine. Okay, so you have this cluster here, this heme group embedded also in then with these other protein units that are going to all make up the overall hemoglobin structure. This would be an example of a quaternary structure. Okay, so here is an example. Let's look at the cartoon down below here first before we go into these tables, because we're going to be talking about the dominant forces in each type. You have the primary structure that looks like that ball and stick, and then you have them wrapped in or somehow arranging themselves into helical shapes, for instance, and they could be even in beta sheets as well. So you have helices, and you also have beta sheets, right? The beta sheets are generally going to have a lot more coils in them, right? A lot more of these helices per se. You have also the tertiary structure, which is just, the protein just getting so big that it ultimately folds in itself. The effect of solvent comes into play, but also other types of bonding. So more of the non-polar has an effect. You have some of the different salt bridges, all that, and then everything gets exacerbated even further if you think about if you have more than one of those blue tertiary structure example molecules there. If you have several of them, in fact, some of them might even be green in this cartoon here that I'm showing, and they're all wrapped in itself. How are they responding to each other? You know, a lot of your quaternary structure, by the way, exists in the body. I mean, you have receptors that look like this. You have the hemoglobin, of course. I'm going to be showing you some other examples of that in a moment, but you're looking at complicated protein arrangements. And the forces stabilizing the structure, if we're looking at the primary, it's going to be the peptide bonds because it's going to be how they're connected. Again, we're not really paying too much attention to the side groups with respect to the primary structure. And even in the secondary structure, we're still not, you know, paying too much attention to those side groups. We're mostly focused on the hydrogen bonding that's occurring along the protein backbone between atoms, between amino acids close to each other and in sequence, okay? Now in the tertiary group, now we start paying attention to all those side chain groups. And you have then a whole variety of the whole spectrum really of the intermolecular forces, from the weakest being the London forces to the strongest being actual ion-ion interactions or ionic salt bridges. And then in the quaternary, you just have the same as what you have in the tertiary, but they're just more of them. And now they're interacting, you know, between each of those different units. So I think that that's important to take away from all of these different examples. Now, here would be an example of a cooked egg, right? So you have an egg, it has the yolk, it has the white, right? Here's the active protein. They just show you this. This is probably ovalbumin. It may not be, so don't hold me to that, but you know, they're looking at the egg white, and I have a great demo that I'm going to want you to watch because we actually look at this at the effect of egg whites whenever they're stressed out due to different stimuli, I should say. And you have this active protein here. It has some non-polar character. It has some polar character, as you can see, because you have some of the coils, you have some of the just the straight chain. So you know that there's a lot of different forces at play here. You also know that whenever you heat it up, it pretty much becomes, well, cooked, right? And it becomes easier to handle, right, to eat if you're going to eat this with a fork, I mean, or a spoon even. I mean, it's really challenging to try to grab a hold of that egg white alone with just your fork or your spoon and trying to eat that. But here, you know, once it's cooked, obviously it's more amenable to being handled and then of course eaten. So there's a lot of other things that can give rise to the smoothness of that. You know, you're basically disrupting some of that structure that it had already existed. And then, you know, we just call that denaturing. You denature the protein, you basically reduce those intermolecular forces. Now it becomes more compliant and you're able to manipulate it. So that's the end result of having something with denatured. Now, I am gonna want you to watch these videos, and these are really important. I think they're pretty cool videos too. There's 5 of them. They're all about the egg whites, and I'm gonna show you the denaturation of the egg whites, but not using heat, okay? We already know that we can scramble eggs and that we can get it from a liquid state into that solid state. And the solid state basically just reflects the, you know, the lack of any kind of intermolecular force that would even keep it stable. And it also, of course, reflects the absence of a lot of water. But in the egg white demo that I show you, I am discussing about all the different tertiary structure that helps gives it its shape. And the main protein is ovalbumin within the egg white, and the egg white accounts for about 67% of the overall egg content, okay? And I give you a lot of really good description and detail in those YouTube videos, not only in the video itself per se, but also in the description, so please read that. It manifests tertiary structure, and whenever you cook it, that tertiary structure becomes lost a bit. It's vulnerable to the denaturation, as it were. So this is really important because everything with tertiary or quaternary structure is able to be destroyed, essentially, or denatured. And this is why, for instance, one of the problems of having a high fever is that you risk that some of your proteins, especially in your brain, they're going to start to become denatured, and your brain will go to fluff, right? It'll just, you know, it won't respond as well, obviously, as a healthy brain. So that's one reason why, if you are sick and you have a fever, you got to keep yourself cool because you don't want to have your proteins denaturing. Denaturing is bad, okay? So I give you some different examples. I have 3 different stimuli. One is just going to be the physical agitation, like if you were going to make egg whites, right, and you needed to whisk it, right? And here you have that and the disruption that you're trying to create with the physical agitation is going to be the hydrogen bonding. With respect to adding in some ionic salts, and here I added in a bit of sodium bisulfite. Okay, so please take a look at this. This nice foam was able to be created, interrupted both the hydrogen bonds and some of the ion dipole bonds as well. And then whenever I used copper sulfate, something else happened, which was really cool. Instead of getting any kind of phase that looks like either the foam in the middle or even that nice bubbly clarified looking liquid on the left, here you have a slime. And so what happened here is that copper actually was able to interact with the egg white and actually denatured it. It combined with the sulfur that exists in some of the side chain groups and created copper sulfide particles. It actually is a redox reaction. And in doing so, it interrupted not only the H bonds and the ion dipole, because I still physically mixed all these things, but it interrupted the disulfide bonds that were already linked in that ovalbumin structure. So please check out this video. Look at the descriptions of each one. These are really important examples, and they help drive home what happens whenever proteins can become denatured. Here's another example. This one is actually from your book. Here you have disulfide bonds broken via ammonium thioglycolate, okay? And this is, or glycolate, however you want to pronounce it, right? You have reduction going on, okay? This happens if you have, hair as is, but then you want that to be reduced, right? This is straightening of the hair, and then you have the oxidation by hydrogen peroxide can reform the disulfide bonds at different hair positions. If you wanted to get, for instance, I don't know, a different kind of look, if you wanted to have more of a permanent kind of structure. But if you want to take all those alpha helicity, kind of looking, structures, you're trying to interrupt that. You're going to interrupt it if there are disulfides, and that's how you can interrupt it. You can get, straighter linkages. You're basically denaturing the hair. It can go back the other way, of course, as well, but there's only so much you can do until the hair wears out, right? But that is just another example of denaturation, and especially among females, right? Males too, I guess. I mean, I don't want to, say that doesn't happen, but whatever you feel like, whatever you want to do to your hair. So the disulfide covalent bonds formed via hydrogen peroxide, okay? But also that hydrogen peroxide is kind of damaging a little bit to your hair as well. So got to be careful with that. Here's another demo that I have, and again, there's 5 videos in this series because there's a lot of different things to talk about. This is really important, okay? The denaturation of dairy milk with acids. So we could also heat up milk if we wanted to, okay, to denature it. But in this particular case, I didn't want to do that. I just wanted to have milk, and I just wanted to add a couple different acids to it. So just to let you know, this actually folds back into chapter 8 material. Dairy milk is a colloidal substance. It has about 80% casein of the protein and 20% whey proteins. So the protein content goes about 80 to 20. This is way different for bovine milk, like I have here, than it is in human milk. So human milk, like, it would have about, I don't know, it's almost flip-flop. It's almost like 30% casein and 70% whey, okay? So in humans, the breast milk that would be about 30% casein, 70% whey, way different than the dairy milk that we drink. The casein proteins are water-rich micelles, and they are globs. Okay, and again, they hold about 3.5 times water for each of the casein molecule. Okay, so if you can think of, if it's 1 gram, that's going to be 3.5 grams of water. If it's going to be 1 kilogram of casein, it's going to be 3.5 kilograms of casein. Okay, casein proteins hold a significant amount of calcium phosphate. These clusters are really important because these are thought to deliver important calcium phosphate minerals for bone growth, right? In the infant, well, it's not even an infant at that point. Well, I guess it is if the infant, the offspring, the child, whatever, not only, during pregnancy, but of course after pregnancy where nursing is occurring, you're trying to establish those nutrients into the new infant, into the new offspring. You know, if it's a cow, it's going to be that calf. If it's a human, right, you're going to have it with the baby. In any case, the casein functions as a storage protein. It's going to help communicate that important calcium phosphate material that will be able to help deliver bone building and tooth formation too, right? I mean, anywhere where you're going to have some bone-like material in the body, and that includes enamel, right? All that helps with that. But it's mostly with bone formation. You got to form the skeleton. You got to reinforce it. So all of that is super important. So the casein that is delivered has about a 10-to-1 ratio, right, of calcium phosphate for every 1 casein molecule. So it's hugely powerful in its ability to retain calcium phosphate and water. I'm talking about the casein protein. Now, I show you just snapshots here where I had whole milk, and then I either treated it with vinegar or citrus acids from a freshly cut and then squeezed lemon. And it's really interesting. It doesn't, because milk is colloidal, because it has these distinct protein phases, these protein phases exist in that solution as a colloid, and therefore also do not exist as having any kind of tertiary or quaternary structure. So that's really interesting. It's also interesting because it's easier to potentially separate them if you were to apply some kind of stimulus, whether you were gonna heat it up, or by virtue of what I did, I used some acids. And you have whole milk and you have skim milk. The difference between whole and skim is the fat content. And you will notice that the curdling is going to especially be pronounced for the fat-based milk, okay, higher fat content. Although you can probably see it better in the skim milk just because there's less fat there, so it's more easily seen the ability of the acids to actually separate out the casein from the whey. Now, interestingly, the denaturation process is different for vinegar than for citrus acid. So that was before filtration. Take a look at this. Look at the clarifying liquid that's able to pass through after I applied the vinegar to the milk. You have this coagulated mess that sits up in top in that filter paper there. And by the way, guys, this casein is the same stuff that is the essence of cottage cheese, yogurt, and also any other kind of cheese that will eventually be formed if you were, then, to have additional processing, okay? Like the addition of maybe, I don't know, some lactobacillus bacteria, maybe you have some rennet in there, just different things. But we're not making cheese, of course. But here you have the distinction that the vinegar this isn't all vinegar, guys, because I only added 10 mils, and this is like almost like 40 mils of the fluid that was able to actually separate out from the milk. That right there in that clarified vial here, this actually is just a cylinder, it's just a graduated cylinder, is whey. Whereas if I added the citrus acids to the milk directly and then we were able to try to filter it, it's a mess. You don't get nearly as many conglomerates there, and it's not as clarified. So citrus actually acts differently on milk than does vinegar. Vinegar has acetic acid. The citrus acid fruits have citric acid. Acetic acid responds to the casein globules differently than the citric acid does. Citric acid is going to be especially active with respect to the calcium phosphates, not so much with the casein globules. Whereas the vinegar and the carboxylic acid, acetic acid is going to be especially adept at being able to interact with that casein and dehydrate it essentially. And in doing so, those clumps are more readily formed from the species. You can see that it's the same whether it's the whole milk or the skim milk. Again, read the descriptions and watch the videos because I think that this is a pretty interesting study. It shows that not all acids act on milk the same way, but it also shows that there are dispositions to what, to the nature of the proteins that are in milk. It further distinguishes it from, for instance, eggs, which have tertiary structure, and it's just another neat way of showing denaturation. So pretty neat. Another example here, here's a summary, forces and examples of each one. Here you have, heating. Of course, everybody knows and is familiar with heating because food is often cooked, okay? Hydrogen bonds are broken, hydrophobic interactions. Those are the kinds of forces that are being acted upon. acids, bases, ionic compounds, as soon as you start adding additional agents or things that are going to be a little bit more involved, then you're going to have a greater ability of interrupting some different types of forces. For instance, you need to have reducing agents that can interrupt disulfide bonds. Here in the example, they have thiols, which are used in hairstyling for hair straightening, or permanent waves, right? So all of that it has to do with the disulfide bonds, but I even told you that using copper sulfate, for instance, actually acted upon a bit, kind of like these heavy metal ions, like silver, lead, and mercury in the middle of this table, well, middle to low end of the table, where it says it interrupts the disulfide bonds. It does the same thing too. Usually you're going to have reducing agents there as well. So this is where, yeah, mercury and lead poisoning, one of the ways to try to suck that out of the body or to sequester it, as you might call them, is eat some eggs. Eat some eggs, or, especially the eggs, because milk, as you saw, does not have all that tertiary structure, but eggs do. And eggs can respond to mercury, lead, just like how they can with copper, and they can kind of surround that, encapsulate that so that you don't allow those heavy metals to be incorporated into your body. This is another reason why, sometimes that is suggested as an approach. If somebody did get some kind of poisoning, first you would try to sequester it, and then you would, take something as an emetic, something that would make you vomit up and then get that stuff out. This is also a reason why, if you have a car and you're having a hard time with keeping coolant in the radiator, sometimes you can add some egg white to it, because that'll help gum it up. That tertiary structure that the egg has, in particular with respect to the egg white, will be able to gum up that environment and be able to allow for an opportunity for fluid to be maintained within that radiator so that you can keep your car cool. You wouldn't be able to do that with milk, because milk is colloidal, and therefore it also then lacks that tertiary structure that we just talked about. Mechanical agitation can also do some things. Detergents, okay? Membrane proteins. Guys, this is really important, because in chapter 11, when we talk about DNA, you're going to find out, I have a demo where actually we take some DNA from fruit. Maybe some of you have already seen this or done this before. The detergents, because they have that polar head group and then that fatty acid tail, well, they're able to interact with any kind of membrane, and that includes cell membranes. And this is where this says the hydrophobic interactions are especially disrupted with respect to the protein membranes, and oftentimes those membranes are phospholipids, right, or glycolipid proteins, or maybe just glycoproteins. Anyway, they are definitely susceptible to hydrophobic interactions, and that's one of the reasons why detergents are used, because the fatty part of the detergent, or that tail, can interact there, whereas the polar head group can interact with the water or that surrounding solvent to try to, keep everything fluid and try to, extract that, or I should say disrupt the cell membrane. So there's a lot of different aspects of this that can lend itself to very creative ways of denaturing something in order to obtain a certain endpoint that you're looking for, I guess. So if you want to, and I say that because, if you want to straighten your hair or permanent your hair, you can denature and then, reconfigure structure of the hair proteins. If you want to extract DNA from a cell, you just need to disrupt the cell membranes. If you want to create a certain type of consistency of an egg white, for instance, you might use not copper sulfate, because that's just, well, that's not going to be good health-wise, to make that and then eat that. But you might want to use a copper bowl that has been freshly cleaned and polished, so that maybe some of the copper that is in the bowl can interact in a unique way with the egg white as it's being beat. Some of the French chefs have even introduced this kind of style of egg white preparation, and that is one of their secrets, because they get little tiny, forms of copper sulfate that do develop. Why? Because the copper pulls the sulfur from that egg white, from the ovalbumin, and in doing so, it just interrupts some of that tertiary structure just enough to be able to get that consistency to be where it is desired. So a lot of different ways to look at these things. So I think that what we'll do, we will come back for the final part of this chapter, and where we talk about the different protein functions. And I had just mentioned before, like in the casein is used as a storage for calcium phosphate like material and also protein, nutritive stuff that can be passed along from the mother to the infant, right? For skeletal growth, for just general protein and nourishment, right? But there's other things as well. And so we're gonna be taking a look at that with respect to the final webinar. So just stay tuned, and we're getting there, but definitely watch those videos and read the descriptions with respect to those videos, and we'll go on from there.